Um, I put a second problem set up. Those have been a little slow coming. They're going to pick up a little more now. That wasn't by design, but um, anyways. Um, so this problem set that's up is a three-dimensional structure, and I would recommend, if you haven't gone through those structures practice problems yet, to go through those, at least once, feel comfortable with those before you start working on the homework. I think it'll make a lot more sense. Um, I have it listed as due a week from today, but I can be flexible with that. Um, and also, I don't quite know what's going to happen Thursday. I don't. I might have to take the day off. I'm trying to find daycare type options. Um, so check your MetNet accounts. Um, like Wednesday sometime. I'll have a note sent out to you, an email sent out to you by Wednesday. If we're canceling class, I guess I probably will just not send anything if there is going to be class. Yeah, I don't know. He's not super patient in a lecture format. Yeah. I've been trying to sort of think outside the box and stuff like, oh, I could pre-record a video lecture and then like come in every 20 minutes and ask if you have questions and stuff, but that just seems like maybe a little unnecessarily.
You got Skype, right?
Skype, yeah. I could do it on Skype. Um that would work extraordinarily badly, I think. Since you can't see the you wouldn't be you just see like my hand moving on the board and just you wouldn't be able to read anything I was writing. All right, so anyways, I need to figure that out. Yep.
About the problem set, could you draw the picture again? Because I'm looking at the picture going.
Oh yeah. Okay, so problem set number 2. Um, so I think first think of so the coordinate system is like this. It's all 3D like. X, Y, Z. Okay? So X is sort of going into the page, Y is up, and Z is to the right. And then based on that, you have um, those are the directions that 3 of your members go out from this point. So uh, you got that, and that. This one doesn't go up that high. And then I don't know why I put arrows on those. Those are sides of a. And then you just finish that tetrahedron. So um, that's the like hypotenuse of this right triangle. Um, and then lines go from. So if you got this right triangle that's down on the XZ plane, I don't know why that looks so messed up, but that's just lying right on that XZ plane, and then you just draw edges from there to the top. Okay, you get a little cheese wedge with this face here is in the plane of the page. Okay, the bottom side is the XZ plane, and then you have this diagonal face. Does that help?
I was a little bit worried, like where is hinge and where is floor?
Oh,
That's what I was like.
okay.
I don't see it.
Okay, the XZ plane is the floor. So if I remember right, there's a hinge that would let it rotate about the z-axis. Okay? So if there was nothing but that hinge, it could just spin around the z-axis, you know? And then there is uh, um, and then there's just like a single contact point. You know, like you could think of it as a ball, like a ball bearing or something, acting probably at this corner. I don't remember exactly where. And that's the thing. What? Okay, at that far corner here. And that's the thing that keeps it from spinning. Okay. And then you're applying uh, loads to this diagonal face. You're applying loads to this face. Do you have that up right now?
Yeah.
What does it say about the loads?
What do you mean? There's 4 vectors. Oh no, that's the places. A force vector of you have the XYZ coordinates of it.
Okay, and it's just at a point? Is it just acting at this point? I think I was originally going to do it as distributed loads, and then I changed it.
It's applied to the ball and socket joint A, which A is the top, yeah.
Okay, so then you just apply the force vector to here. But also, all of these members have weights. So you have to, so they each have weight applied to them too. Okay, does that help at all? I mean, really, so in this class, you know, you're trying to get the skills to do three-dimensional problems, but you never do many three-dimensional problems for exactly this reason. It's just so hard to draw, you know? Like, so even in the book where they use, you know, more sophisticated graphics and stuff, it's pretty hard to convey a lot of times what's happening in the three-dimensional picture. But hopefully this one will make sense.
Okay, so so the z-axis is kind of resting on the floor.
The XZ plane. Yeah, the Z-axis and the X-axis are both resting on the floor.
Guess I'm not quite understanding why there's a hinge there. I don't see how it moves.
Okay.
How it could possibly move.
Well,
Okay, so let me draw a few views. I think that'll help. So let's first, what does this thing look like if you're looking sort of straight on the ZY plane? Okay, so we're just looking straight at this front face. Then the body that you see is a right triangle. And you put a hinge here, okay? Actually, that's not where, I think I said it's at the, I said it's here, right? At the origin. So that's supposed to be like a realistic drawing of a hinge, you know? Like a little pin sliding through some supports. And so now this wedge of cheese can rotate around the z-axis, okay? And so for this thing to be static, if you're applying forces to it, we need something else to keep it from spinning around that hinge. And that something else is just a single frictionless contact. You can think of that as a ball bearing applied over at this corner.
So the XYZ is not touching the floor?
The origin is touching.
Oh, just the origin.
The origin is, and the x-axis is on the floor, and the z-axis is on the floor. The y-axis is going out of the floor.
In that whole side, there's nothing
Underneath. This whole thing is solid. Wait, no, it's not. What am I talking about? No, it's a truss. Right, there's nothing underneath it. I mean, it's just, how many sides are there, edges in a truss? 1, 2, 3, 4, 5, 6?
Talking about the hinge, just how it looks like it's propped up from the ground. Is that what you're talking about?
Well, it says the plane is on the floor, and you have this hinge and a ball on the other side. It seems like if you remove the ball, it would just fall onto the floor, or if it's touching the floor. I guess I'm
right.
missing.
Okay.
That's the part that I was questioning.
Okay. Okay.
XZ plane is on the floor and there's a joint to hold it there, but if
Right.
that joint wasn't there because it's loaded on the other side, it would flip.
So so when I say that that plane is on the floor, I'm ignoring the fact that this hinge maybe is a centimeter high and the ball bearing is a centimeter. You know what I mean?
Yeah.
So I guess technically they'd be, if those things are touching the floor, then really this coordinate system would be a centimeter up from the floor. Does does that make it more confusing or less? That's what I want you to tell me from now on when I answer your questions. Just tell me, is it more confusing or less confusing now?
So if the hinge has 0 height,
Yeah,
it's resting on the floor.
right.
But why does it need the pin on the other side?
Why does it need the ball on the other side?
Yeah.
Okay, because if all of these three members were just resting on the floor, like that's sort of the alternative you're talking about. Why do I have any joints at all? This thing's just resting on the floor. It actually is a statically indeterminate system. And in order to solve it, you'd have to calculate deformations, which we don't do in this class. Okay.
So the only points of load are at C and B.
Uh,
Ground.
here
Yeah,
and
so I
here.
guess that's what.
That's right. Yeah, you can't solve it unless I
Those
give
are
you
the
a more
only low
specific
points.
place for context. That's right. Right. For reactions.
Their reactions
Yep.
from the ground.
Right. And then there's this force here. Yeah. And you're trying to calculate, right, the reactions between the members.
So D isn't touching anything.
I don't remember how I lettered it. This is D.
So D is out there, yeah.
Yeah, that's right. D is just off the ground. Yeah.
Yeah.
Any other questions? Okay. Well, last time we started talking about calculating internal loads. And so I'm going to start with a problem for you to do. We'll sort of do it in steps. Like you'll do a step, we'll come back, make sure that you're on the right track, then we'll go back. And so we'll kind of solve it in pieces like that. And then I'll talk about what we do when we have distributed loads, okay? Because so far we've only talked about point loads. And then we'll do another problem in the same format where we'll break it into pieces. You'll do it. We'll come back and do it together. You'll do the next piece, come back. We probably won't finish that one today, I would guess, but maybe we will. Okay, so here is the first problem. You have this long beam. You have a 10,000 Newton force applied here where this angle is 45 degrees. And you have an 8,000 Newton force applied here where this angle is 30 degrees. And the dimensions you need are 1/2 meter here and 1/2 meter here. Okay, so let's think about, we want the formulas, say, and the diagrams, which are just graphing those formulas, that represent the tension, the shear force, and the bending moment as you move along the length of this beam. By the way, what's a beam? In statics and deform and any mechanics class, it's sort of interesting to know that a beam, like, you think of a beam as like an I-beam, right? Like, once it's manufactured, it's a beam. Maybe it's sort of longer than it is thick or something. But in mechanics, a beam is a long, relatively slender. So that part is the same as when you talk about a beam just in everyday discussion. I don't know if you do that. Relatively slender member. With loads, so this is the part that's different than the way we're used to thinking about beams. With loads, at least some loads, let's see, how do I want to say this? With at least one load besides forces along the length. Okay, so what this means is when you do truss problems and you neglect the weight of the members, remember then those are two force bodies and all you have are forces acting from one joint toward the other joint, okay? Then those aren't beams, okay? Even if those members are made by an I-beam company, okay? Those aren't beams the way we talk about beams. In order for something to be a beam, you need a third force, or you need a couple, okay? You need some kind of lateral load or a couple. And what are the steps for doing this? What do we have to do to solve this? Yes, thank you. What? Yeah, okay. And actually, before we do that, so the steps that I gave you last time are for when you already know all the external loads on the body. This one we don't know all the external loads. So the first thing we're going to have to do is just do this as a single body statics problem. Figure out what the external loads are applied here and here. And then we can go to that list that you're thinking of. Okay? Then once we have those external loads, we identify the important points, make one cut, draw the free body diagram, use Newton's second law, rotational Newton's second law, get the formulas, go on to the second cut, and so on. Okay? So, step one, or I guess I probably numbered those steps before. I know I have a bad habit of giving you a nice numbered set of steps and then using different numbers when I talk about it again. So I'm going to call this step 0. That's a common strategy I employ to fix that. Find the reactions at the pin and roller. Okay? So draw that free body diagram, use the equilibrium equations, and solve those values. And when you're done, we'll do it back up here.
Is that 10,000 at 0.25?
Yes. Yep.
Okay.
So you hear that? So this 10,000 Newton force is halfway between the pin and the roller. I'll be right back.
Can we assume that they're all acting at the same points?
That what?
They're all acting at the midpoint throughout the. That makes sense?
This and this?
Yes.
Nope. You can't do that. You could if this was a particle problem, but.
Like on the thickness?
Oh, yeah.
Okay.
I thought you were asking if you could apply these all as like a particle problem when you're calculating these reaction loads. Okay, good. I'm glad you weren't asking.